have lesson 2 yet? I gave it to you yesterday, right? If anyone doesn't, it's over there in the little thing there. If anyone wasn't here yesterday. Okay. So we're going to talk about the periodic table today. All right. Periodic tables range into 2 main things here. Groups. Groups are the vertical columns that go up and down, of course. We're going to talk about the specific names of those in a little bit here. So group 1 is like, for example, the alkali metals, if you remember from last year. Group 2 is the alkaline earth, etc., etc. We'll talk about that later. And periods. Periods are the horizontal rows on the periodic table. And we should get our periodic tables out today as well. All right, so I'll let you copy those. Whatever. Okay, metals are found to the left of the staircase. Non-metals are found to the right, and metalloids, of course, are straddling the staircase. All right, so we'll give you a little second to copy that down, and we'll chat about that. All right, so once again, metals are to the left of the staircase. The staircase is in orange there, of course, on your periodic tables, which you should get out today, is in black there. So non-metals are to the right. We have metalloids, what we call metalloids, like things like germanium, arsenic, antimony, tellurium, polonium. If you don't know the periodic table song, go look it up on Google. It's really cool, it's catchy, and you will never forget it. Okay, once it kind of burns right in your mind kind of thing. You'll be singing it all long weekend. Check it out though, seriously. But those are metalloids. So they have properties of both metals and non-metals, and sometimes behave more like metals, sometimes behave more like non-metals. Depends what they're hooked up with. And I'll show you a nice little chart at the end. I can't wait, it's my favorite one. It's a graph, it's got lines. It's got temperatures, it's got boiling point, it's awesome. Oh, I can't wait. Stick around for lesson 15 in this unit, okay? It's awesome. So we'll talk about that and how they behave with different types of elements there. I kind of gave you the answers here already. I'm not sure why this is still on here, but that's okay. Just take a look at your periodic table real quick here, and we'll talk about that. Grab the... Okay, I think just to save some time here, we'll kind of work through this together here. You need to get your periodic tables out here, first of all. And before you start writing stuff down all crazy here, I just want to show you something. So obviously, in each element here, we got some numbers. We have different things that are in each one. It's obviously the symbol, the name of the element. But also take a look at what else is there. And if you're ever confused about what these other numbers are, look in the top middle here. We got an example of, iron, I guess. Okay, so it tells you the atomic number, which of course you guys know is the number of protons. So iron's got 26. It's got a atomic molar mass, it says right there in grams per mole at 55.85. The most stable ion charge, one of the most important things you have to remember for this class is the following. The iron comes in a 3+ and a 2+, of course. The most stable one, or the most common one, I should say, maybe, the most common charge of iron that it forms when it wants to lose electrons is the 3+. You know that because it comes first in that little square there. So there's a 3+ and a 2+. The 3+ is the most common one. Okay? Make sure you know that. So when we talk about double replacement reactions towards the end of the year here and whatnot, and we use those, it always forms the most common one, or the most common one, which in this case, iron has a 3+ charge, is the most common. It can form 2+, not as common. All right. Electronegativity, we're going to talk about in this unit. Okay, and what that is, we're going to give you a definition. We're going to use that extensively. In this case, electronegativity is 1.8, and of course the symbol and the name of it. Okay, so that's what's all in this here. What's the atomic number for bromine? Let's find some bromine here. What's the atomic number? 35. Sure. So let's put that in there. What's the symbol and normal state of krypton? Krypton's what's the abbreviation for, what's the symbol for krypton? Kr. Okay, don't get krypton confused with kryptonite. They're different. All right. States. States. How are you going to know the states? Well, this is where you get to do some homework perhaps this weekend here. And if you want, you don't have to. All right. I like you. You just seem like a happy-go-lucky guy. All right. If you want to know states, and if you're not sure, once again, you might have to go to the data booklet and look that up online and check this out, because it's on there as well. Your periodic table doesn't have colors, and like I told you before, just messes it all up. So if you want to know states, here's what you need to do. You probably need to look over here for the time being. By the end of this semester here, but towards the end, you'll know all of them off by heart. Okay, I guarantee you. anything in gray writing, so potassium, calcium, scandium, titanium, vanadium, all those, anything with gray writing, not the outline, the gray writing here, for example, okay, is a solid at room temperature. All right? There's only two liquids at room temperature, and that is mercury and bromine are the only two liquids that we have at room temperature. That's not to say that you can't make it a solid or a gas, but at room temperature is 25 degrees Celsius, we assume. Okay? So at 25, all the gray ones are solids, blue one, liquid. The red ones, okay, nitrogen, oxygen, fluorine, neon, argon, chlorine, blah, 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 and hydrogen are gases. All right, so krypton in this particular case, we look over there, it's in red writing, so we'd probably say it's probably going to be a gas at room temperature, normal state of matter. Okay. One element has a symbol of Nd. It's way down at the bottom there. You got to find it. It's in the very second bottom row there. It's called neodymium, and its molar mass, so 144.24. Grams per mole. All right. Most common charge of lead. So to find lead, you want to look for Pb. Now, don't get lead confused with peanut butter. All right. Because Pb. Because peanut butter is good, lead's bad. Okay. So yeah. Pb. What's the most common charge? So find lead there. It's what, number 82. The most common charge, of course, is the first one, so 2+ would be your correct answer for that. And like I said, we're going to talk about electronegativity down the road here. Rhodium is Rh. To find rhodium, it's number 45. And if you want to find the electronegativity, just look up, I think it's right above the symbol, if I'm mistaken. So it's 2.3. Okay? So the reason I gave you that there is just so you kind of know what's in that square. And if you forget what's in the square and what each thing is, there's a little legend at the top there for you so that you know, and it tells you what each one is. All right? You guys have a little bit of copying to do with these. So group 1 is called the alkali metals. So make sure you write that down. Make sure you spell it properly as well, please. Group 2 is called the alkaline earth metals. I'll let you write those two down, and we'll talk about each one of those in a sec here. Okay, so group 1, alkali metals. It's important to remember this all the way to the end of the year because we'll often ask you questions about, like for example, at the end of the year, maybe on the final exam, which alkali metal is the most reactive or something like that. Well, if you don't know where the alkali metals are, if you're not sure if it's group 1 or group 2, that's going to be a little bit of an issue for you. So make sure you know these terms. Eventually I'll give you a quiz on this, but not for the next little bit here anyway. Group 1 are soft and silver. On Monday, Monday you're not coming here, I don't think. Well, if you do, teach yourselves. Tuesday. On Tuesday, we're going to go to the lab and I'm going to show you group 1 metals. They're soft and silver, so I'm going to cut them open for you. I'll show them to you. They're the most reactive of all the metals. Reactivity increases as you go down the group. All right, so if you look at group 1 there, we got lithium, sodium, potassium, rubidium, cesium, francium, or sometimes francium. Depends on who's talking. Francium's the most reactive one, all right? And I'll show you why in a second here. Those all have something in common. That's why we put them there. They all have one extra valence electron. Do you guys know valence electrons? You should, because there was a definition on it the other day. They're the electrons that are in the outermost energy level, right? So they all have one, and that's actually why we group them together, because they're all very similar in that regard. All right. They easily react with water to produce hydrogen gas in a basic solution. That is actually part of a single replacement reaction, which you guys know from last year probably, yes? Maybe. We're going to do some more of those this year, so don't worry if you don't. Who's seen lithium in water? 1. Who's seen sodium in water? Who's seen potassium in water? Who's seen rubidium in water? Put your hand down. Who's seen cesium in water? Who's seen francium in water? Well, it's pretty much not possible. So, so yeah, we'll show you that on Monday or Tuesday. Stick around for Tuesday. Tuesday's gonna be fun. It's cool. Don't ruin it and look it up. Okay, trust me, it's funner. It'll be more funner when we do it on Tuesday. So we'll show you what's happening there. It's going to produce some hydrogen gas in a basic solution. I'll show you both of those, and you'll be able to see that. I like to do it on the next day because we do a little bit of review that way, and also it kind of breaks up a whole chunk of 80 minutes of me talking. That's boring, right? Soft and silver. Let's talk about why reactivity increases as we move down. So let's get a little chart out here. We're going to do some, you guys, apparently a lot of you have done Bohr diagrams before, eh? It's true? Yeah, good. That's good. And if you haven't, don't worry about it. We'll do it again on a Tuesday probably. But Bohr diagrams, let's take a look at something here. Let's take a look at lithium for a second. Lithium is atomic number 3, so we need 3. You should know this for your, not the diagram, just the numbers. You should know this for your quiz on Tuesday. 3 protons. And we got 7, a weight to 6.94, so 7. So we should have 4 neutrons. You can write this down if you want to. It does explain why reactivity increases as you go down the group. So it kind of just reaffirms that. How many electrons can you put in the first energy level? 2. All right. Did you guys use dots last year? Okay, well, we should use dots to represent electrons. So we'll put 2, 1, 2. Those are my 2 electrons there. How many can go in the next one? 8. How many do we need? 1. Okay. So 1. All right. So there's an example. That's an example of a Bohr diagram. We'll do those again, like I said, Tuesday. So don't freak out yet. But those are important. We need to be able to kind of draw those and represent what lithium looks like. So we got our nucleus, protons, neutrons. That's where all the weight is. We got the electrons orbiting, all good stuff. Okay. Now let's go to francium. Let's just go right to the bottom. Francium. Francium's number 87. 87 protons, and it's got a weight of 223, I think. So it's 136 neutrons, or as I like to call them, jimmies. I haven't used that joke yet? Oh, okay. But it's still funny though, isn't it? Eh? All right. You didn't laugh yesterday? Oh, so you made up for it today. Okay. I'm going to cheat a little bit. I'm not drawing 87 dots. I'm telling you right now. There's no way. Okay, so 2, 8. How many go in this one? 8. Maybe we've talked about this already. How many go in the next one? 18 is correct. How many go in the next one? Eventually, yes. How many go in the next one? Come here, I'll show you something. How's it going? I like you too. You're nice and quiet. How many go in the first one again? 2. 1, 2. Yeah? How many go in the next one? 8. 1, 2, 3, 4, 5, 6, 7, 8. Yeah? Right? How many go in the next one? 8. 1, 2, 3, 4, 5, 6, 7, 8. How many go in this one? Count them across. 1, 2, 3, 4, 18. There's 18. Trust me. Okay? How many go in the next one? 18. How many go in the next one? No, I tricked you. You think so, but no, because look, 57 to 71's right here. So that's actually these here, right? So how many go in that one? Well, actually, if you counted all those, 1, 2, and then 3, 4, 5, 6, 7, 8, 32. It says so right there, actually. 32. Okay? And then, so now we did 30, what did we do here? 18, we did 32, and how many do I need in the last one? How many? There's 32. How many do I need in the next one to represent francium? 1. Because francium's the first one over. See? Now, let's go write that down here. What did I say? 18. So 18, right? 32 and 1. Okay? That's what francium looks like. ran out of room. I wish smart boards were smart, or I wish they were twice as wide. Widescreen. So that's the difference between these two. Now, what do metals want to usually do? This should be hopefully a little bit of review from last year, not you, somebody else. What do metals want to do to become more stable? Sure. Yeah, metals want to lose electrons, right? So here's my one electron here. Look at, oh, before that, actually, I kind of jumped ahead here maybe. What holds the electrons in the orbit, for example, around lithium here? What holds that? What prevents them from just kind of leaving, just going somewhere? You know? What holds these two, well, actually these three electrons in this orbit here around there? Electrons are negative. Protons are. Electronegativity is correct. Really, it's something as simple as basically protons, electrons, right? So we got some positively charged protons in here. Opposites attract. Basically, you'll learn. This is a lie, so this is just kind of funny. But you'll basically learn everything in this class is about opposites attract. Just think about that for prom. Dating. Chemistry is like basically dating class. No? Bonding. Opposites attract. Chemistry with one another. Fine. All right. Look at the distance there. Look at how, the protons are in the nucleus, right? They're not going anywhere. They're in the nucleus. Look at the distance there. How well do those three protons attract those three electrons? Especially, more specifically, how well does it attract that farthest outside electron? Pretty well, right? It's pretty small distance for the most part. Not too bad. How well do these attract this particular electron here? Pretty good, right? But look at francium. How well do these 87 protons attract that electron way out there? Not very well, right? I mean, look at the distance it's got to go to attract that far outside electron. So which electron is more easily lost? Is it lithium's or is it francium's? Which one is more easily lost? It's francium's, right? Right? Yes? No? Right? Look at the distance. So which one, therefore, is more reactive? Which one is more easily to give up that electron to something else? It's francium, right? Where does that electron usually go? If I can get rid of this electron, does it just go off into space? Where does the electron usually go? Yeah, usually what kind of atom, actually? Yeah, usually a non-metal, because what do non-metals want to do? They want to gain those electrons. And that's how we get charges on stuff, and that's what we're going to review next week as well. Okay? So francium gives off that electron very easily. Okay? If there's any kind of non-metal, it'll most certainly get rid of it. Okay? It'll give it to that non-metal. So francium is the most reactive metal. And as you move down group 1, reactivity increases. Okay? All right, let's go back to here for a sec. Group 2 is the alkaline earth metals. They're light reactive metals that form oxide coatings when exposed to air. I'll show you that on Tuesday. Stick around, it'll be fun. Calcium is a very good example. I'll show you magnesium too, but sometimes that's hit or miss. Calcium, always guaranteed. Calcium forms an oxide coating around it, so when you look at calcium, you think it's a metal, right? You say, oh, it should look like a metal, like, this here, for example, or should be kind of shiny or whatever. It's not. It's very dull looking, actually. And that's because that oxide coating is formed around it to prevent it from further reaction. So it actually looks, calcium metal looks white, usually. And I'll show you that. And in fact, we're going to dump that into some water as well, and I'll show you the difference between group 2 and group 1 on Tuesday. When you dump calcium into water, you know what happens? Nothing for a little bit, because it's got to get rid of that oxide coating before it can actually react calcium and water. Okay, so it takes a little while for that oxide, that white layer, to come off. And then once it does, you'll see what happens. It blows up. No, it doesn't. Okay, we don't do that here. It's not that fun, all right? Like I said, they're not as reactive as group 1 because they have to lose 2 electrons. They're still reactive though, okay? And like I said, I'll show you that on Tuesday. Next, 3 to 12, transition metals is what we call those. Transition metals, I'll let you guys write that down. Now, transition metals, 3 to 12, so groups 3 to 12, that's kind of the middle part there. It's, you know, there's lots of different metals in there, so we just kind of group them together. They don't really have, like group 3 doesn't share a ton of stuff that's in similarity to each other. Group 6 doesn't, kind of thing, but 3 to 12, there's so many different properties in there. They can be multivalent, so they can form more than one charge. For example, we talked about earlier copper. Copper forms a 1 plus and a 2 plus. If we didn't, we just did. Chromium forms different charges. Cobalt has 2 different charges that are common. Lead's not really in that 3 to 12 group, but still lead is in that kind of area there. It forms more than one charge. So when we get to the naming part, which will be next week again for a review, same thing. It's you're going to have to be a little bit careful with anything from 3 to 12. You have to be careful because usually includes Roman numerals, if you remember, for naming ionic compounds. We have to make sure we're using the right charge and whatnot. We'll talk about the metal ductile stuff later. Halogens, group 17 is the next one we focus on. Okay, the halogens. They're the most reactive of the nonmetals. And reactivity is the opposite. It increases as you move up the column. And once again, we know nonmetals, want to gain electrons. They want to become more stable. So let's take a look at some nonmetals here, like for example, fluorine. Fluorine is the most reactive nonmetal. Okay, it is the top right, basically. It's got 9 protons. It's got 10 neutrons. We got, well, I can draw them, I guess, 2. And that's probably a mistake. Well, whatever. Let's just do 7. Okay, I'll cheat a little bit here. So it's got 2 and 7, 9 protons, 9 electrons. It's the distance thing again. It's the electronegativity thing again. It's all that stuff. But remember, the 9 protons are trying to attract, you know, those 2 and the 7, of course. And if we had an electron out here, floating out, let's say right there, how easy does 9 protons attract that electron that's not too far past that second ring there? Fairly well. If we kind of compare that to, let's say, bromine. Bromine is what, 35 protons, 79.9, so what is that, 80, so 45 neutrons. We got 2, we get 8, 8, and 17, I believe. Okay, 2, 8, 8, all the way across would be 18, so 1 before is 17. Okay. Now, by the way, I'm going to tell you right now, you might say, some of you guys might say, do we have to know how to draw, you know, bromine as a Bohr diagram and things like that? And the answer is no. Okay. When you get to that next layer there, there's little suborbitals and things like that, and that's not grade 11 chemistry. That's not even a little bit, well, it's not even grade 12. You won't even do it in grade 12 unless you take an AP course. That's, I'll tell you what grade that chemistry that is. That's grade 13. Okay. First year of university. All right, there we go. All right. So if I say it's grade 13, you don't really have to worry about it for the rest of your time here. All right, or next year. So it looks like that. Well, how easy does 35 protons attract out to here? Not too bad. How well is it going to attract out to there? It's going to be a little tougher. Okay, it's not going to pull in that electron as well. Therefore, if it can't pull in that electron as well, it's not going to be as reactive. It's not going to pull in that electron very easily. It's not going to be as reactive. So we have to remember that fluorine is the most reactive nonmetal that we have. So it's kind of the 2 spectrums. We've got francium in the bottom left. We've got fluorine in the top right. Okay, most reactive metals, nonmetals. Reactivity always increases as you go up. Okay, and we'll talk about electronegativity and all that other stuff as well. Okay. I'll show you some other neat stuff with that electronegativity stuff too, okay, eventually. So it's the opposite for that. All right, let's move on here. Group 18. Oh, by the way, let's go back to this for a second. Why does fluorine want to gain that electron? No, not you. Somebody else. Anyone else? I don't care. Why does fluorine want to gain an electron? Why is that so? Sure. Yeah, so it has a full outside shell. So all the electrons in the outside shell are filled up, right? That's the basis. That's why do we find sodium and chlorine together, sodium chloride, right? Why do we find that together? Because sodium wants to give up electrons, right, to become more stable, to get rid of that one extra electron it has. Chlorine wants to gain that one electron. That's how ionic compounds are formed, right? Magnesium chloride. Magnesium has 2 valence electrons. If it could get rid of those 2, then it would become more stable. It would go back to being like, we say, noble gases, right? So if you look over here, you know, we talked about lithium before. If lithium can get rid of that 3rd electron, right, that one in the outside energy level, it becomes more like helium. It becomes more like a noble gas. It has a full outside shell, right? It becomes more stable. If we go back to here, I'll show you. Okay, so pretend this one electron isn't there. Well, how many electrons do we have in the outside energy level now? We have 2, right? There is only one energy level in this case, but we have 2 now. If francium can get rid of this 1 electron here, we'd have 32. It'd all be filled in the outside energy level. It'd be more like radon. Okay. If fluorine can gain 1 electron, now it becomes more like, it's not going to lose 7. Okay, that's pretty tough. For fluorine to lose 7, I mean, that's a lot of electrons to lose. It's a lot easier for fluorine, if you look there, to gain 1, it becomes more like neon. All right. Bromine becomes more like krypton when it gains 1 electron. That's what makes them more stable. Okay, they're always trying to become more stable. That's not to say that lithium, you won't find lithium by itself. In other words, is there such thing as lithium atom? We get confused later down the road here. Is there such thing as just lithium atoms by themselves? Absolutely. I'll show you on Tuesday. I'll show you sodium by itself on Tuesday. All right. But if it has a chance to become more stable, to get rid of that electron, it will. Okay. All right. Moving on here. Group 18. They're kind of boring. They're the noble gases. They don't react. They're really, really low chemical reactivity. They have a full outside shell. So why do they want to react with something? They don't. Why would you? We're happy, right? We got a full outside shell. What am I going to do? Give up electrons to become more happy? No, because I have a full thing. Do I want to get any more? No, I'm happy. I'm good. Okay. And basically, they already have a full outside shell, valence energy level, we call it, of course, et cetera, et cetera. Okay. Okay. I think we're doing okay for time here. Let's do this. We can do this. Okay. I will at some point in time ask you for properties of metals versus nonmetals. Did that turn out at the top there? I'm not sure when mine didn't, but anyway. There we go. Okay. Properties of metals versus nonmetals. So these are 4 things that you want to know. Most metals, if you look over there, are solids at room temperature. The one exception, of course, is mercury. Nonmetals tend to have much wider range of properties. There's solids, there's liquids, there's gases over there. And that'll be the same when we talk about ionic versus molecular compounds later on. So make sure, for 1 mark, this is what I want to see, exactly this. Metals are solids under room temperatures. Nonmetals can be solids, liquids, or gases. Okay? Don't tell me that metals are solids and nonmetals aren't. Okay? Because that's not true. Metals only exist as atomic elements. So you're walking down the street and you're like, hey, look, it's potassium. Or when we go to the lab on Tuesday, I'll say, hey, look, it's potassium. Potassium exists as you could get 1 atom by itself. In other words, yes, they're usually linked up a whole bunch, but you could find 1 potassium atom by itself when you're walking down the street. Non-metals can be by themselves, like carbon, for example. You'd find one carbon by itself. But other ones, we talked about this the other day, would tend to hook up to become a little bit more stable. So things like oxygen and nitrogen and fluorine and chlorine and bromine, right? The molecular elements. So non-metals can be either atomic elements or what we call molecular elements. Okay, you're not going to get that molecular elements with the metals. It's not going to happen. Metals tend to be shiny, bendable, malleable, ductile. In other words, you can work with them, you can mend them, you can hammer them, rearrange them kind of a little bit. We'll talk about why later in this unit. I'll show you that on Tuesday as well. Non-metals tend to be dull and brittle. When we talk about non-metals, probably my most favorite one to compare is carbon. Think about carbon. Where do you know carbon? Well, carbon is your pencil, right? They tend to be not very shiny, okay? Dull. Press too hard, you can break it. Okay, so that's an example of a non-metal there. Metals are good conductors of heat and electricity. You hook up, for example, whatever, a piece of metal to some heat, or you start heating up a metal, it's going to get hot. They conduct heat and electricity very well. Non-metals are poor, and sometimes not at all conductors of heat and electricity. All right. Metalloids. Last one here, I don't know if we'll get this done here, but metalloids are the elements found between the boundary that distinguishes metals from non-metals. Metalloids have properties of both metals and non-metals. Some of the metalloids, such as silicon and germanium, are semiconductors, which means they somewhat conduct electrical current. All right? And the list, I'm just going to finish this here, guys. The list of metalloids include boron, silicon, germanium, arsenic, antimony, tellurium, polonium. If you don't know the periodic table song, go listen to it over the weekend, YouTube it. It's fun, it's catchy, and you'll sing it all long weekend. I promise you. All right? And I think that is all. So, we'll stop there.